All right, hello everyone. I hope you are all doing well. In this video, I'm going to go over how to do full truth tables. We use full truth tables when we don't know the actual truth values of any of our atomic propositions, that we represent with capital letters. And what full truth tables allow you to do is to calculate every possible truth evaluation for some given well-formed formula. So it allows you to map out all the conditions under which a given well-formed formula will be true and will be false, okay? And then what we can actually do is compare well-formed formulas together to determine whether they are logically consistent, logically inconsistent, logically equivalent, or logically contradictory, okay? And I'll be going over all of those terms momentarily, describing what all of them mean and everything. But for now, let's go ahead. Which page am I looking for here? This one. Okay, go ahead and share the notes here. All right, so I mentioned this in the last video, but it's worth going over again as far as the order of operations goes, okay? So whether you know the truth values of some of your atomic propositions or not, you need to go in this order, okay? So you start, once again, with capital letters that represent atomic propositions, okay? Now, the next thing that you want to calculate are tildes immediately preceding sentence letters. Then you look at logical operators that appear in bound parentheses. Okay, so these would be what you could call secondary operations, right? So if you've got two sets of parentheses, then any operators which fall into a first set of parentheses, which it means it would be sort of double bound, that would not be the main operator, all right? The main operator is always going to either be a tilde outside all of the parentheses or an operator that is only within one set of parentheses, okay? Now, then you look at tildes immediately preceding parentheses, and then the last thing you want to calculate is the main operator. So the main operator is whatever operation is determining the truth value of the entire complex proposition, whatever that proposition is. Okay, so a good sort of strategy or rule of thumb is right when you start examining a well-formed formula, it's usually good to isolate the main operator. So the first thing you should do before you even start writing ones and zeros in your table, locate the main operator and say, all right, this is what I'm going to calculate last. Because if you get the main operator wrong, you're going to be looking at the wrong operation to determine the truth values of the actual propositions, okay? All right, now, but every truth functional statement itself is going to fall into one of these three categories, okay? So a well-formed formula, a truth functional statement, is either going to be logically necessary. Now, what that means is that under every possible truth evaluation, the statement turns out to be true. Now, how that would look in an actual truth table is if a statement is logically necessary, that means you're going to have all ones underneath the main operator. So if under every truth evaluation you get a 1 underneath that main operator, that means there are no conditions in which that proposition would be false. So under all possible truth evaluations, the statement turns out to be true. So if under all possible truth evaluations, the well-formed formula turns out to be true, that means it's necessarily true. Okay, now other propositions are going to be self-contradictory. So if you've got a truth functional statement which is self-contradictory, that means there aren't going to be any conditions in which it is true. So that would mean you would have all zeros under the main operator. So under all evaluations, this statement turns out to be false, which means that it's a self-contradictory statement, okay? So in bivalent logic and truth functional logic, in logic that corresponds to the law of non-contradiction, self-contradictions are always false. Okay, so there is debate about whether or not there can be true contradictions, but there can't be any true contradictions in the system of logic that we're using right here. But there are philosophers who think that under different kinds of conditions other than bivalence and non-contradict, the law of non-contradiction, there actually can be true contradictions. We're not going to get into that. All right. So if you've got all zeros underneath the main operator, that means that that statement is a self-contradiction, right? Now, most statements are logically contingent, meaning there's at least one truth evaluation where the statement comes out true and at least one evaluation where the statement turns out to be false. So if you've got at least 1 under the main operator and you've got at least 1 0 under the main operator, that would be a contingent proposition. Okay. All right. Now let me switch over here to the practice sheet. All right. Now, doing truth tables in Microsoft Word is incredibly infuriating, so I cussed a lot making these tables. All right, but I tried to get them to match up as best as I could here. Okay, so let's start here with this formula. So this says either it's not the case that T only if B, or T and not B. All right, so either it is not the case that T only if B, or T and not B. Okay, now, so in this formula, in this statement function here, let's just look at what the main operator is. So we've got a set of parentheses, the main set of parentheses here. We've got, a bound set of parentheses here. Okay, so this is the main, or this tilde is the main operator of this formula. And here, the conjunct, the dot, is the main operator of this formula. Well, this wedge, right, the either or, this is what's sort of binding the entire formula together. So the truth value of this whole statement is represented by the wedge. It's represented by the either or, okay? Now, and in order to fill out a table, okay, so I've already provided all the lines here for you, but if you're starting your own table, how to determine the number of lines in a table is the equation L, lines, the number of lines, equals 2 to the nth power, all right? So L, the number of lines in your table, equals 2 to the nth power, where n is the number of letter types that you have, okay? So there's a difference between a letter type and a letter token, okay? So in this formula, we have letter T and letter B. So those are our letter types. We only have 2 letter types. Now, but obviously we have 4 letter tokens. Why? Because we have 2 T's and 2 B's. Okay, so N doesn't refer to the number of individual token letters that you have. It only refers to the number of letter types that you have. So we only have 2 letter types. We have T and B, but we have 4 individual letter tokens, right? So don't count the total number of letters as far as, so if you have 5 instances of P in your formula, that doesn't mean, okay, well, this is going to be a really long table. If you have 5 instances of P and 1 instance of Q, you've got 6 token letters, but you've still only got 2 letter types, okay? Now, so since we have 2 letter types, 2 to the second power is 4, so that is why we have 4 lines in this table, okay? Now, and then to calculate the number of consecutive ones and zeros that you write under your first letter, in this case, which is T, and then our second letter is T. Take the total number of lines and then divide it by 2, okay? So under T, we're going to write 2 1s and 2 zeros consecutively, all right? And my font changed, but I'm not gonna go in and change it, but whatever, okay? So under T, we get 2 1s and 2 zeros, okay? Now, to find the number of consecutive 1s and zeros under B, take the number of consecutive 1s and zeros under your first letter, which is 2, So there's two consecutive ones and two consecutive zeros under t, right? And then divide that number by 2 again. So 2 divided by 2 is 1. So under b, we're going to get 1, 1, and 1, 0. So 2 ones and 2 zeros under t, and then 1, 1, and 1, 0 under b. Okay. Now, and since you have these values over here, this is what you can do. And I am on the exercise assignment, I actually designed it this way so you can do this. Now, you can just use this over here as a reference in filling out the table, or if you want, you can actually fill in those values under T and B you want to. So you're not required to do it that way. So if it's easier for you to just look over here and say, okay, well, this would be a 1, 1, 0, 0, you're going to do that. Okay, now, but I'm going to go ahead and fill out the whole table just for those of you who might want to have everything, right in front of you like that. Okay, so we've got 2 1s and 2 zeros under T, okay? And I've got 2 instances of T in my formula. So here, you got to make sure that those values match up to what I have over here, and then same with this one. Okay. All right, and then we'll fill in the values for B as well. Okay. All right. Now, notice over here we've taken care of all of our sentence letters. Okay. Now here we've got a not B, so that would be the second thing that we do. Okay. Now here you can actually skip a step. So keep in mind that since the value of the tilde is going to be opposite whatever B is, so B is true, false, 1, 0, 1, 0. Okay, well, not B is just going to be the opposite, 0, 1, 0, 1. Okay, now what you can do, you can also fill in the values for B, but in the actual table that can look a little crowded here. So if you just want to fill in the value of the tilde, feel free to do that. Okay, I'll leave that up to you. So again, if you want to fill in the values of B and then fill in the values of the tilde, be my guest. But if it's easier for you to just fill in the value of the tilde, that's acceptable as well. But just make sure the value of the tilde for a sentence letter is exactly opposite whatever the value of that letter is, okay? So it would be a mistake to have something other than 0, 1, 0, 1 in this column here, which represents the tilde. Okay, now, what do we calculate next? The next thing we calculate are logical operations bound in parentheses, okay? So we have the horseshoe here, and we have the dot here, the conjunct here, okay? So the value of the horseshoe is going to be determined by the value of T compared to the value of B, right? So the value of this horseshoe is determined by the value of T compared to the value of B. Okay, now the value of this dot is calculated by comparing the value of T to the value of this tilde. All right, so since the tilde is an operation, so the value of the tilde is determined by the value of B. The value of the dot is determined by the value of T compared to the value of the tilde. Okay, so it would be a mistake to compare T to B over here because we've got an operation, right? We've got a negation in front of B. So we're not asking, is T and B false? No, we're asking, is T and not B true? Okay, that's what we're asking, all right? Now, and this is where the shortcuts come in handy, all right? So since this is a horseshoe, there's only one condition where a horseshoe is false, and that's when we have a true antecedent and a false consequent. So in all other circumstances, this is going to be true. So this is true on line 1 because we've got true antecedent, true consequent. It's false on this second line because we've got true antecedent, false consequent, and then it's going to be true on all of those other lines. Okay? All right, so we've got the horseshoe. Now, and remember, the only condition where a dot is true, right? The only condition where a dot is true is when both parts of it are true, okay? So the only place where we have that T is true and not B is true is on line 2 of the table. So here we've got true and false, so that dot is going to be false. Here we've got that T is false and not B is false, so that would be false. And here we've got that T is false and not B is true, so that would also be false there, okay? Now, step 4, we've got tildes immediately preceding parentheses. Okay, so we've got a tilde over here, and what is this tilde actually negating? This tilde is negating this horseshoe. So whatever the value of the horseshoe is, the value of the tilde is going to be the opposite. Okay, so under the horseshoe, we've got true, false, true, true. So this tilde would be, whoops, false, true, false, false, right? So false, true, false, false, okay? Now, and then the last thing we have is our main operator, this wedge, this either or, okay? So to find the value of the either or, all right, we compare the value of the wedge, or I'm sorry, the value of this tilde to the value of this conjunct, right? We are asking if either this is false, which is represented by this, or this is true, okay? So either it's not the case that if T, then B, or it's the case that T and not B, okay? So the value of the wedge is determined by the value of the tilde and the value of the conjunct over here, okay? So here we have false or false. So either this is false or this is false. Well, this half is false and this half is false. So that's the one condition where a either or statement or a disjunctive statement is false. So a disjunct is false when both parts are false. So this part is false and this part is false. So that gives us a false disjunct. Okay, or here we have true or true. Okay, so that will be true. False or false. Okay, and then false or false. Okay, so what does that tell us? That tells us there's only one condition where this is going to be a true statement, right? There's only one condition where this is going to be a true statement, and that's because there's only one line in our table. There's only one line in our table where this wedge turns out to be true. Okay, so this is going to be a true statement anytime T is true and B is false. In all other circumstances, this is going to be a false statement. Okay, now, but what kind of statement is this? All right, well, this statement, this whole thing is true on line 2 and false on every other line. Okay, so that means there's at least one circumstance where it's true and at least one circumstance where it is false. So this is contingent. This is logically contingent. There's at least one evaluation where the statement turns out true and at least one evaluation where the statement turns out false. So this is a logically contingent statement, okay? Okay, now let's look at this one. All right, so here's what we have. R, if and only if not B, only if it's not the case that either T or not B. So R, if and only if not B, only if it's not the case that either T or not B. Okay, Now, so notice here we've got a longer table. We've got a table with 8 lines instead of 4. Why? Because we have 3 letter types. We've got R, B, and T, right? So we've got 3 letter types. Okay, so to determine the number of subsequent or consecutive T's and F's. Yeah, see, I did it. Ones and zeros. We're not using T's and F's. The number of consecutive ones and zeros under R. So take the number of lines in the table, which is 8, divide that by 2, and we get 4. So under R, I'm going to do 4 ones and 4 zeros. And those are really big numbers, but yeah, because it's at 6, I'm just going to leave it, okay? Now, so our next letter is B. So we've got 4 ones and 4 zeros under R. So we're going to take 4 and divide it by 2. That will give us 2 ones, 2 zeros, 2 ones, and 2 zeros under all of those lines, okay? And then our last letter is T. So we can take 2 ones and 2 zeros and divide that by 2. But since T is the last letter, that's just going to have 1 1 and 1 0 the whole way down, those 8 lines. Okay. Now, and again, I'm going to go ahead and fill in the letters here just for the sake of simplicity. Okay, let's do that. All right, so I really hate that the formatting changes, but you know, that's fine. I'll just do a lot of clicking here. All right. So 4 ones, whoops. 4 ones and 4 zeros under R. All right, that's the only instance of R we have, okay? Now, these are both negated B's, so we'll do those secondly, okay? And then we have T right here. So 1 1, not a minus sign, 1 0, 1 1, 1 0. Under this instance of T, okay? Now, so we've got our just sentence letters that don't have any tildes here, and we've got 2 instances of B. We've got 2 instances of B that are negated. Okay, so again, you can fill in the value of B and then fill in the value of the tilde if you want, but I'm just going to fill in the value of the tilde. So if B is true, true, false, false, true, true, false, false, not B is just going to be the opposite. So false, false, true, true, false, false, true, true. So false, false, true, true for that instance of B, and false, false, true, true, false, false, true, true under this instance of B. Okay. Now, probably should have started here. So what is the main operator? So again, we've got R if and only if not B, only if it's not the case that either T or not B. Okay. Well, this triple bar is bound by 2 sets of parentheses. This wedge, again, is bound by 2 sets of parentheses. This tilde is negating this wedge. So that means that our main operator is this horseshoe. This is the main operator right here. So that is going to be the operation that we calculate last. All right. Okay. So doesn't matter whether we do the wedge or the triple bar first. So we'll just go in order. All right. So remember the shortcut for the triple bar. The triple bar is true just in case both parts of it are true or both parts of it are false. Okay, so on lines 3 and 4 of the table, we have that the triple bar is true. And on lines 5 and 6 in the table, we have that the triple bar, both halves of it are false. Okay, now on every other line, we've got true, false, true, false, false, true, false, true. Okay, so the triple bar will be false on lines 1 and 2, and then on lines 7 and 8. Okay. Now, the shortcut for the wedge, there's only one condition where a wedge is false, and that's when both parts are false. Okay, that only occurs on line 6. Whoops. So on line 6 of the table, the wedge is false, but on every other line, that wedge is going to be true. Okay. Now, this tilde is determined by the value of the wedge. So I'm saying it's not the case that this whole thing is true. Well, again, this whole thing is represented by the wedge. So there's only one line where the wedge is false. Well, that means there's only one line where the tilde is true. On every other line, this tilde is going to be false. So for the wedge, we've got true, 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 false, true, true. So with the tilde, we're going to have false, 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 true, false, false. Okay? All right. Now, how are we calculating the value of the horseshoe? The value of the horseshoe is determined by the value of the triple bar and the value of this tilde. So to find the horseshoe, compare the column with the triple bar to the column of the horseshoe, or I'm sorry, the value of the tilde here. That's how we find the horseshoe. Okay, now, and remember the shortcut. The only time that a horseshoe is false is when the antecedent is true and the consequent is false. So the triple bar is the antecedent, the tilde is the consequent, right? So the triple bar is the antecedent of this conditional. This whole thing is a conditional statement. So this is the antecedent, this is the consequent. So compare the triple bar to the tilde. All right, now on lines 1 and 2 and on lines 7 and 8, the antecedent is false. So a false antecedent is enough to give you a true conditional. Okay. Now, on line 6, the consequent is true. So once again, that is enough to give you a true conditional. So a conditional is true just in case either the antecedent is false or the consequent is true. So a conditional statement is true just in case either the antecedent is false or the consequent is true. Okay. Now, on lines 3, 4, and 5, we've got a true antecedent and a false consequent. So this conditional is going to be false on all of those lines. Okay? Now, and I wonder if I can highlight this column. Borders, no, that's the border. Okay. So, if it's easier, go ahead and highlight that column so you can see what it is. All right. Now, so under the conditional, we have true, true, false, 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 true, true, true. Okay. So there's at least one line where the statement is true and at least one line where the statement is false. So once again, this means that this is a contingent proposition. Okay. All right. Now, the reason why highlighting can help is just so you know what you're looking at. So you know that this column right here under the horseshoe indicates what the actual truth value of this entire proposition is. Okay. All right. All right. Now, I'm going to go ahead and split this video in two, just for the sake of brevity. Okay. So in the next video, we will talk about comparing propositions, comparing truth functional statements and determining whether they are consistent, inconsistent, contradictory, or equivalent. Okay. All right. I will see you all in a little bit.